Hi everyone, this is worksheet 15.2, entropy from the partition function. This one should be an interesting one. Okay, so let's begin. You saw that the internal energy from a statistical perspective is the average energy of the energy levels that the system could take. And another way to write this is to say that this is a sum over all of the energy levels, the probability of the system being at a given energy level times the energy of that level. All right, so if we've got a small change, du, in internal energy, then that means that it could come from either a change of the probability or a change of the energy level itself. And we did this in an earlier video. And it's going to be a sum of a small change in the probability of an energy level times the energy of that level, plus a sum over all the energy levels where the probability of a particle of the system being at that level remains constant times a change in the energy level itself. And I told you on the previous video that this is heat, which we could call dq. And we'll say that it's a reversible change in heat because that's going to be easier for our purposes. And this is, of course, counterpart to heat, work, or dW, reversible, like that. Okay, and you remember from chapter 5 that a small change in entropy is equal to a change in the reversible heat divided by temperature. That's the second law. So if we can find out a statistical mechanical expression corresponding to this one right here, then we'll be able to find the entropy. Okay, so we are imagining a system at temperature T and energy levels E sub I. Okay, and we want to remember our definition for beta is 1 over kBt, like that. And in order to get a statistical mechanical description of the entropy, we're going to consider the function f, which is going to be a function of beta, and then also of each of these energy levels, energy level 1, energy level 2, energy level 3, so on and so forth, all the way up to all of them. And f is going to be equal to the log of big Q, which we have seen before. And this just equals the log of the sum over all of the Boltzmann distribution over all of the system energy levels, like so. And so a way to depict this is we've got a series of energy levels in the system, and you might wonder, don't the molecules have energy levels? Yes, they do, but the system has energy levels as well, and in general, the system is going to have energy levels that are displaced by some random amount. So notice they're not random, but to some unpredictable amount, and that's what I'm trying to depict by having these energy levels separated by arbitrary distances. And it doesn't matter really for this derivation what those distances are, because it's all going to work out just fine. All right, first let's find the derivative of f with respect to b, keeping all of the energy levels constant. Okay? This, of course, is just going to be 1 over the sum of all the energy level of the Boltzmann distributions of all the energy levels times a sum of the negative energy levels times the Boltzmann distribution of those energy levels, like that. And hopefully you remember that this is just the negative average energy, which is just the negative internal energy. So that's the derivative of f with respect to beta. But now what if we get the derivative of f with respect to some energy level j, all right, where beta and all of the other energy levels are kept constant? And if you perform that derivative, then we still get q put on the bottom here because of the derivative of that logarithm. But now it's going to be times negative beta E negative beta EJ. See, because it was a sum over all of those energy levels, a derivative with respect to that one energy level does not result in a sum right here because it was just that one energy level. Yeah? And so we can say that this equals negative beta times e to the negative beta EJ divided by a sum over I of the Boltzmann distribution of all of those other energy levels. Yeah? And this part of the expression right here is just the probability of energy level J. Hopefully that looks familiar. So we can say that all this just equals negative beta times the probability that the system exists at energy level J. All right, if we want to construct a total differential of F, then this is just going to equal partial F with respect to beta d beta, and we're keeping all of the other energy levels constant, plus a sum of all the energy levels, df dei dei, and we're keeping beta and all of the other energy levels constant, except the one that we're actively summing up right there. And we already found this. We saw that this equals negative internal energy, and this right here is just the probability of energy level I. And so we can say that this equals negative U d beta minus beta summing over all of the probabilities times some change in the energy level. And maybe you recognize this expression from the top of this worksheet. This is d work. Great. So we're ready to move on to the next side of the page. Okay, here we are on the next side of the page. Let's consider a change in the internal energy times beta. Okay, this is just going to equal internal energy remaining constant times a change in beta plus beta remaining constant times a change in internal energy. And this sort of just follows from the product rule of calculus. So we could say that a change in F plus a change in U times beta just equals negative U d beta from the other side minus beta, a sum over all the energy levels, probability of that energy level times a change in the energy level, plus U d beta from up here plus beta du from up there. And you'll see that these two just cancel right out, and we're left with beta times a change in U from right here minus a sum over the energy levels probability dei like that. And we can say that this just equals beta times a change in internal energy minus that change in work right there. Right. Now, if you remember your first law, this right here should equal the heat. And we're assuming that both of these are reversible. Therefore, this whole expression just equals the change in reversible heat divided by kT, which, as you know from the second law, is the change in entropy divided by K. So therefore, a change in entropy equals K dF plus U beta. And since F is equal to log Q, we can say that ds is equal to K d log Q plus d Ku divided by Kt, because we moved this K on the inside right there, and the K's just cancel out. And if we get rid of the D's, the derivatives, then we can just say that the entropy is equal to K log Q plus U divided by T plus some constant, and it turns out that the constant just equals 0. And that's it. That is the entropy of the canonical ensemble. But we know from the microcanonical ensemble that entropy equals the log of W. And this is in the case of constant number of particles, constant volume, and constant energy. And this is actually the microcanonical partition function. So therefore, I could say that log Q plus U divided by KT equals the log of big W. And so if we want to convert between the canonical and microcanonical partition functions, we can do that. If I raise e to everything in this expression, then we end up with Q e raised to the internal energy divided by KT equals the microcanonical partition function. Or another way to write this is that Q equals the microcanonical partition function W times e to the negative U divided by KT. And remember that this big W is the same big W that we saw back in chapter 5 to represent the number of ways to arrange a system under constant energy conditions.